Okay.
C version.
Oh, okay. Yeah.
4.5 and 4.5. Then you have to do something like satisfy the constraints. That's the hardest part.
Okay, so did anyone think, I put up some questions yesterday, did anyone think about the question about the exponentials? So I was telling you that if a hiking algebra is a lattice of exponentials and such a thing is distributive, and then I also told you that y to the x in a Boolean algebra can be defined as x complement join y. So, and I said this is an exponential. So does that mean I didn't really have to require distributivity?
No.
So I can't tell who's speaking. Raise your hand. Ah, okay.
I think you need distributivity to actually do that.
Yes, right, exactly. To show that this is an exponential, you need distributivity. So one way to say it is, yeah, so I can sort of bundle up the distributivity and showing that something is an exponential. Then I have the structure of an exponential and then the arguments I did before go through. But of course, I need the distributivity, so I don't really need those arguments. But it's sort of a thing to think about, right? So that's the idea. So you have to check. So you should check this. As an exercise, you should check that when you check that this is an exponential, that you will need distributivity. Okay, so that's important. Okay, good. All right, so that's just a little side remark. Okay. So the other thing I had last time is I raised issues just to remind you. So as a reminder, we're sort of puzzled a little bit. I will shortly, I think, resolve this puzzle, but we're puzzled by what should be this notion of equality that I've sort of encouraged us to think about. Okay? So the equality or the equivalency notion that I was writing. And I proposed a possible criterion for thinking about equality, and in general this will be in a context. Okay, so we can write there. And I posed some criteria, and one criterion I suggested, basically out of nowhere in the context of the development I've been giving, that you would want this notion to be analytic, meaning that given gamma m, n, and a, it should be self-evident that m is equal to n or equivalent to n in this sense. Well, why? Well, at this moment I can't justify that. Okay, I'm not in a position to do that, but I will be momentarily. Okay, so we'll see how that goes. All right, so that was just a reminder for us. And we define, for example, to remind us of what the issue is, we define a type of natural numbers. Okay, so we define nat to have, there I think I spelled it out, something that's tried to be consistent. So which has a zero, a successor, and an iterator, or sometimes recursor, I'll call it rec nat. Okay, and I pose you as an exercise the distinction and ask you to derive that as an exercise. So I'll leave that alone. So we're written by that. I won't repeat the rules here. And then we showed that we can define various things, but one thing that's very easy to do is define plus, okay, which should have the type of what you would think, okay, and you want to define it so that it does addition. And one way to do that is to simply define it as lambda x, lambda y, and then we're going to do a recursion eventually on y. Okay, when y is 0, the answer is x. If you tell me x prime plus y, then I will tell you successor of x prime. Okay, and the idea is that inductively this will represent the sum of the predecessor in y, and then I add one more, and that will be the sum of the successor in y. So in particular, we get the theorem, calling it a theorem, a fact, a proposition. Okay, so a fact, okay, which I mentioned last time, a version of, okay, it's the same thing, is that for every m and n that are natural numbers in our meta theory, I can certainly get something like this. Okay, that is that. Here's the theorem. Yeah, plus mn is plus nm. That would be something I can do, or in fact, what I should do before I do that is put in the middle, let's say this is the sum, the numeral corresponding to the sum, and then Okay, so I can easily prove that, and I do that by mathematical induction. Okay. So the point is that proof is required, as trivial as it may be, but a proof is required. I have to invoke induction to prove this result. So we then discuss to what extent to some kind of equations of this figure, something of this form, to what extent can that be internalized inside of type theory. And so I'll point out a few things that you'll also be able to prove. I'll just jot them down here. And a few things that you won't be able to prove, and these are going to prove to be very annoying, either when you do, or if you do, or if you already have tried to work with this sort of a type theory. One of the things that's monumentally annoying is dealing with equality. And it comes up in the following way. So for example, I will be able to show, you will be able to show, in fact, I'll write it in this manner. You will be able to show that given x and that, plus of x and let's say 0 is x. You don't even need to know what x is my point. It's going to be a variable, okay? And you will be able to show that given x in that, and given y in that, for example, that plus of x and the successor of y, you'll be able to show that that's equal to, according to our notions of equality right now, okay, plus whatever it's supposed to be. Okay, you'll be able to show that. And the reason is that these require only beta-like reasoning. Okay? These require the beta rules. If you just take the definition of plus I gave, assuming I didn't make a mistake, maybe I did, if that's correct, then whatever the right code is, if you crank it out, you will just be able to calculate that this is true. So in a certain sense, you can say these facts are true by calculation. Okay, that's just a way of saying it. Okay, just by virtue of calculation. The kind of thing that can be very annoying is the status of this thing. If you look at plus, on the other hand, 0x, you're not going to be able to prove this to be equal to x, okay? Unless you have that eta rule, which requires a proof by mathematical induction as a premise. But then what you're doing is reducing it to essentially what I've already shown you here, okay? So if I have an evidence-free, so this is not the case without the unicity principle that I gave you, which requires mathematical induction, okay, to show it, okay? And many people, and it's perfectly understandable, many people, and by the way, the analogous thing, you will not be able to show successor of some, I guess I should call that y prime for symmetry. You will not be able to show that this is the successor of plus and y prime and x. Okay, because this will not be the case without the unicity. Okay, unless you have that unicity principle. And there's a host of things. I can start going on and on and on. But you will quickly realize, and in actual fact, if you look at standard formulation of AGDA or anything based on this sort of type theory, it is not the case for neutral. For neutral, these are ultra equations. Neutral is in certain respects radically different from those type theories. And so, but in the sort of type theories we're working with right now, this will not be the case. Okay? The other thing that I will mention about this unicity, but the unicity has the problem that it requires evidence in its premise and proof by mathematical induction, and it wasn't clear what to do with that evidence. And I'll come back to the nature of evidence and the importance of that momentarily, but I just wanted to remind you and set up a few things. The other thing that you might find a little bit surprising is that these two things, okay, you might want to somehow put these together as to some sort of statement about plus, analogous to what's going on here. But the problem is there's no way to write what this is. There's no way to internalize. This is sort of the most you can say about plus in a certain sense, because there's no way to internalize what the answer ought to be. In other words, the sort of correctness thing is, in present development, extremely questionable how you would state it. You see, this is basically a meta theorem, right? Because I'm using my meta mathematics, okay, here, so this quantification is going on in my metamathematics. Okay, and one of the things that really stinks about working with formal systems, which is what we're doing, is in order to work with a formal system, you end up having to do mathematics all the time. And then you think, well, so what's the point of that? And I think that's a very good question. From a foundational point of view, I think it's a complete dead end. You can never get a foundational theory by axiomatics. So you're always stuck with some kind of metamathematics. So we'll get back to that a little bit later. But I just want to give you a few remarks. And especially for those of you who are not experienced, this kind of thing will bite hard. The distinction between this and these two scenarios, for example, will bite you hard as soon as you start dealing with families, which is what I did last time. So what we're looking at is I was trying to explain to you the notion of families of terms. Okay, I'm interested in this, and we're going to need this. And the reason is that, as I mentioned, these correspond to predicates or relations, which are also known as propositional functions, okay, because they're functions that yield propositions, okay. And so via proposition types, we want to be able to deal with such things. A more down-to-earth or programming thing that corresponds to, so from the point of view of logic, then it corresponds, as I just said, to predicates. From the point of view of functional programming, it corresponds to types like seq n, where n is in nat. Okay, so I can use whatever notation I like. The notation I will use for a moment is that for any n in nat, seq n will be a type. Okay, and right now I'm thinking of that as sequences of natural numbers of length n, just to be totally concrete and not ambitious. Trying not to be ambitious and trying to have something that is immediately obvious what it ought to be. I won't axiomatize what that is. I'll give you that as an exercise. You can write down what the introdilume forms of seq n might be. It's enough for me to deal with this. Okay, so we'll just do that. All right, so there's a motivation for dealing with the notion of family of types. And at the first cut, this is the setup I'm going to use. In general, okay, I'm going to need the following. Now I'm going to say something about the general machinery I need to step up to this level, the next level of type theory. So in simple type theory, as I was talking about before, what machinery did I need? I admit that I was not giving you every detail because it's awfully boring for me to write down every rule. I was trying to give you the ideas. And the main ideas are, we developed we had the idea of A as a type, and we had the idea of gamma as a context, which is really a derived notion, but we can do this. And we have the notion of in gamma and as a type A. Okay? And those were the notions we were using. And from this, we can get a derived notion, which is the notion of a substitution, which is just a tuple of terms. If gamma is to be thought of, think of this as x1, a1 through xn, an, and think of this as the thing with prime. So let me write xi prime, colon ai prime. Well, yes, but it doesn't have to be the same length or anything like that. So I'll just use that notation. It just means relative to gamma prime, a term of type M1, a term of type Mn. It's a derived notion. Okay. And the importance of that, I didn't really emphasize it explicitly because I can't say everything, is that we have the property that if we have this and we have that, then I can combine these two things. And we can conclude that in gamma prime, I have this, the substitution. Okay. The point is it's contravariant. Substitution is contravariant. What it's saying is if I can provide values for all of the variables x1 through xn in terms of the variables xi prime, and I have something which makes sense of type A in terms of the variables x1 through xn, then if I substitute according to gamma, then I'll get something that makes sense in terms of the variables xi prime, and it'll still have type A. That's the sort of setup we have in simple type theory. And I gather from erasing the board that Ed was telling you about the structural properties of type theory, and the morphisms between contexts must have come up, and I don't know exactly how he find it, but this should look familiar. Okay? All right, so what happens now in what is called dependent type theory is we're going to have the following sort of apparatus. What we're going to have is a basic notion of gamma as a context, and we're going to have the notion of two contexts being equivalent in the sense that I'm trying to develop. And then we're going to have the notion of a family, which says that A is a type, and relative to that, that A and A prime, let's say, are equal types, which will be set up like that. And then we'll have the notion that M is of type A, and that M is equal to M prime in type A. That is the framework. So this is the framework, and again, we have the derived notion. If we wanted it as a derived notion, which is gamma is a map from gamma to gamma prime to gamma, and a derived notion that two of them are equal. But that's derivable from the things I've mentioned up above. Okay? So in other words, think of it as an iterated substitution. There are more or less abstract accounts of this sort of thing, which make fewer commitments to what gamma looks like, and I don't want to get into every possible nook and cranny of things that can be done and have been done. I want to give you the flavor. So there's lots of nooks and crannies around here. So, all right, but this is the sort of overall architecture that we're examining. And the thing that comes up is, so the point is that this is our notion of family. So this is a notion of family. This we can think of as our notion of context, which can also be thought of as the closed types. And I'll explain why that's a good intuition a little bit later. And then we'll look at that as a notion of element. Okay, so that's the first cut. So as I mentioned, here's an example of this sort of a judgment. Okay. And now the important thing is we have to have the idea of functionality. So if I have a family indexed by A, let's call it B, and I can write B sub x just to be emphatic, okay, type. I expect the principle of functionality, or I demand the principle of functionality, which is where all of your annoyance is going to come in. Okay, so you'll see, I can write it like that, or I can put it, let me just put it in the simplest form. And I have two terms that are deemed to be equivalent at type A, then I expect that family to respect that equivalence. So what I expect is that if I instantiate the family at M, I want that to be the same as instantiating the family at M prime as type. Okay, that's a crucial idea. So for example, it should be the case that sequence, okay, with plus x, I don't care what x is, put anything you like there, any m at all, 0, should be the same as sequence of m, because this is equivalent to that by the previous obscured board, okay? This is equivalent to that, and the sequence being a family of types, okay, from the box on the left, ought to respect that fact and give you equivalent types. Okay, so that's the point. So if I were to write this out, I would say these are equal as types. So a similar property obtains, and I didn't explicitly mention it, a similar property also obtains for elements of a type. So if I have x in A, so let's put it over here so you can see it. So if I have x in A and I have mx is in B or even bx, all right, it can also depend, okay, the element can depend on the index that we're talking about. Oh, and now let's call it P and P prime for the heck of it. All right, so P and P prime are equal as elements of A. And it's also an aspect of functionality that I expect P for xm to be equal to P prime for xm. And, well, now comes the interesting question, okay? Well, where? Well, I have a choice. I could write two things here. I could write m for xp, or I could write m prime for xp. Because after all, I have, I'm sorry, p, it should have been called p, pardon me. So p and p prime. Because after all, I have p and p prime are equal, so what's to distinguish them? In fact, by what I wrote on the left-hand board here, these two things ought to be the same, right? Just viewed independently. If we just look at, so this is set up to imply that for x and a, b of x is a family of types. And then pointwise, n is an element of b for each x. Okay, so that's what that is saying. So we have this as these are implied premise or consequence of the first premise, or there's many, like I said, there's many nooks and crannies, so let's not go into all of that. But this is present. So these two types are equal, and these two things are equal. But where are they equal? I have to choose. So we have this general principle of respect for type equivalence. And it says the following thing. If m is in A, and A is B, or A prime I've been using, so let's stick with that, then m is in A prime. And moreover, if m is m prime in A, and A is A prime, then it had better be the case that m equals m prime in A prime. If I have these two principles, particularly this one is relevant here, then I can choose either because they're equivalent. Doesn't matter which one I write down, because I can switch to the other one by using the type equivalent. Well, okay, so that all makes sense? All right, so the idea is equivalent types classify equivalent terms, and they determine the same equivalence relation for those terms. Yes? Makes sense? All right, so that's the setup. But now I will be able to address with you the issue of why we don't want the unicity rule for now. Okay? The reason is that let's focus on this rule. Suppose you're writing a type checker for this type system that I've defined here. And one of the things you're going to have to do is if I pose you the question, is m of type A prime in some context gamma? Well, one of the things you're going to have to face is you have to invert all the possible rules that apply to gamma m and A prime. You have to invert all of them. You have to look at all the possibilities. One possibility is this very rule. It might be that m has type A prime because it really, so to speak, really has type A, whatever that means, but it has type A, where A is equivalent to A prime. So you have to run this rule backward. When you run this rule backward, you now have to decide whether A is equal to A prime. You have to find an A prime to test it against and to decide whether it's equal to that. Okay? So you're going to have to face the question. The point is that the decidability of type checking will depend upon the decidability of this notion of equivalence. And that, for many people, is the decisive argument as to why this judgment ought to be analytic. And so, because if I include the natural number eta-like rule, the unicity principle, determining whether A is equal to A prime can, by virtue of like the VEC example, a seq example, can require me to try to find an inductive proof. This could be VEC of M, VEC of P, sequence of P and sequence of P prime. And now I have to figure out whether P and P prime are equal are equal, and that equality might require me to use the unicity principle for the natural number. So in particular, a concrete example is I might find myself with the situation where M is a sequence whose type is plus xy. Maybe that's even a variable, so it's indisputable that this is what its type is. And this is what I have, okay? And what I need to show in a given verification will be M is a sequence of type plus yx. So now I have to show, okay, in order to apply this principle, if I included the eta-like rules, then it would imply that I need to show that these two types are equal. To show that those two types are equal, as previously discussed with you, requires me to do a proof by induction, which means that your type checker has to do proof search to figure out whether addition is commutative. Now, when I say addition is commutative, what I mean is the piece of code I wrote on the previous board that I called plus, that thing has to be proved to be commutative. And I could have written down the wrong piece of code, so it's not like a given that it's commutative. And in any case, there's lots of other fancier scenarios that amount to the same thing. I'm just trying to show you something immediately obvious. And you'll discover, so because of that, there are two sort of ways people go. One is to say, I don't care. Okay, the decidability type checking is unimportant. So I think that's a totally valid position. And you can take that position, and this is what New Pearl does. However, I will tell you, and as Bob Constable will explain to you next week, New Pearl is not defined to be that. It's just that New Pearl has the property that, in this scenario, these two things would come out to be equal because those are equal as functions of x and y. They're extensionally equal. Okay? So that's something to watch out for. In the, so New Pearl is an example of the phenomenon of an extensional type theory. Okay? It is not, and doesn't exist in the world, something called extensional type theory of the formal system. That's a nonsense thing. Okay, there's no such thing. Right? It doesn't exist in any implemented system. New Pearl has a completely different foundation. I'll just make one remark to get out of the way. What we're doing here is formal systems. We're defining type systems. These judgments are going to be defined by inductive definitions, which means that the facts that I can prove, for example, if this is supposed to be a proof of a proposition, there's only computably enumerably many such things. But the truths, even in arithmetic, are not arithmetical, let alone sigma 1. So it's preposterously incomplete. And it will ever be thus. Okay? That's absolutely impossible to get at the notion of truth. So if you have a notion of formal proof, which is what is being suggested here, and which motivates this being decidable, you're immediately in the game of coming nowhere near the truth. Then you're a million miles away from the truth. Okay? Because, as I say, even if we confine ourselves to arithmetic, it's no amount of alternation of quantifiers. That is, truth in arithmetic is non-arithmetical. It's an ancient theorem. Okay? And yet everything is sigma 1 because it's just a recursively enumerable, computably enumerable set. Okay? So it's got very, very, very little to do with the truth. So what New Pearl is instead of being a theory of formal proof, which is inevitably off the mark, it is instead a theory of truth in mathematics. So there's a much more profound notion of type theory than what I'm doing with you here. Okay? And so I hope that when Constable comes, you'll get more information about that perspective. These type theories are very, very, very different. And in fact, there are two different propositions as type principle. They get confused and conflated, and all sorts of terminology is used that, in my mind, is completely incorrect. You will see. And so what Constable has done is developed a theory of truth based on Brouwer's conception of mathematical truth. What we're doing here is hacking about with formal systems. Okay? So we should understand that that is what the game is. Okay? So there are various reasons to do one thing or another, and I'm not going to say one is somehow they're incomparable things. Okay? But what I can definitely say is anything that is defined by a bunch of rules in this inductive definition is a million miles off the mark, and it always must be the case. It's the nature of axiomatic theories. They are not really foundational. Okay? They cannot be foundational because they need metamathematics to justify them. You have to find a model to show it's consistent. And where did that model live? Well, in some other mathematics besides the one you wrote down. And how do you justify that mathematics? Well, if you do it as a formal system, then you need a meta-mathematics. And this never ends. Okay. So that's why. So from a foundational point of view, I don't believe in formal systems. I don't think that they're actually getting at issues of foundation. They're useful for lots of things, and we're going to develop that. But I'm just trying to situate them as to, in my mind, of how things fit together. Okay, so for our present purposes of doing formal type theory, merely formal systems, then we want to insist, the usual criterion is to insist that this be a relation that is analytic. I can just determine whether M is of type A just by looking at it. It's never a theorem that something is of type A. It's a matter of grammar. See, what I'm writing down with these inference rules as I write them down is I'm just telling you a context-sensitive grammar for the well-formed terms. Period. That's all I'm doing. Okay? So it's never a mathematical fact that a term has type nat. It's a matter of syntax. Okay? That's the thing to understand. All right? Well, that's kind of, that's useful to a certain extent. But then it's kind of weird, because if it's all just a matter of like saying this is a grammatical phrase, you see, you can already feel I'm missing the point of mathematics. I'm concentrating on grammar instead of concentrating on the math. Okay, so that's the difference between the two sorts of approaches. But we'll stick with this. The systems you're going to use next week are based on this kind of conception. But I would like you to understand that there's a much bigger world, and you'll learn a little bit more about that partly next week. Okay, so we'll insist that these things be decidable, which means we will then deny that eta principle that I talked about with that. So I will now erase this proviso because we'll just deny that principle. And then you will not be able to show that those are the same, and therefore you will not be able to go from here to here just by virtue of the fact that these are the same type. It's going to be a problem. I'm going to show you how to deal with that in a minute. But okay, so do we see what we're doing? So, like us too. I think, you know, there are many opportunities, because type theory is a complicated thing and it's quite an expensive thing. Right, okay. There's ways in which you can, without realizing it, jump to conclusions that are not warranted. I know, because I've jumped to those conclusions. They weren't warranted, so I know what I'm talking about. So what I would like to do is sort of help you not, you know, make those kinds of mistakes, and also to explain to you why is it like that. Why is it that, you know, plus x0 is x, but plus 0x is not? You know, on the surface of it, it looks idiotic. At any rate, but I'm trying to show you there's a reason for all of it. Okay? All right. So, oh, by the way, so when we deny the extensionality principle we had before, then this judgment, in that circumstance, this column represents what is called, I don't like this phrase, I'll call it this phrase, calculational equality. Okay, it's a lot of times it's called definitional equality, or calculational equivalence, because as I mentioned to you, I'm going to end up tripping all over myself with words, because words have lots of meanings, and unfortunately everything comes together in a way here that causes a lot of terminological conflict. So I'll call it calculational equivalence. It's often called definitional equivalence, but I find that ironic because it has nothing to do with definitions. So, but that's what it's called. So the idea is that these are the same by virtue of a calculation. So I will make another remark, okay? Since we are talking about formal systems, and these are going to be defined by a collection of rules, and we're going to say that judgments hold exactly when they do so by virtue of these rules, it means that everything we're doing here, and in particular the notion of calculational equivalence, is quite arbitrary. And I can define, for example, this judgment to simply mean the left and right-hand sides are alpha convertible. They're just rename of bound variables. And I can define it that way, and I will have a perfectly valid type theory. So my point about this is this notion of calculational equivalence is very slippery. It is totally up for grabs. And to my knowledge, there is no theory of what it ought to be. Okay? It's arbitrary. And I'll show you very shortly, once we start enriching type theory and doing more interesting things, I will show you that the arbitrariness of this thing becomes more and more obvious. Okay? In particular, I will make the following claims. A, it's arbitrary. B, it has nothing to do with computation. Okay? Not inherently. Because I could take it to be just the identity relation, the diagonal. And that has nothing to do with computation. C, that means that the type theory I'm defining for you in no way has any computational meaning. It's merely an axiomatic theory. You have to understand that axiomatic theories are arbitrary constructions. Okay? So you just write down a bunch of rules. That's it. So one shouldn't read too much into this kind of type theory. This is quite different from the new Pearl type theory, which you start with the notion of program, and the theory of truth is based on the notion of computation. That's Brouwer's brilliant insight. Okay? It's a whole other ballgame. Okay? So I would say be careful. Okay? So there's nothing on the board that talks about running programs. There's no cost model. There's no deterministic evaluation strategy. There's nothing useful from the point of view of programming. Okay? Very important to understand this. Okay? So, all right, I can impose a computational interpretation on certain fragments of this type theory, but it is not inherently computational in nature. That's the thing I want to say. In direct contrast to Newbrook. Okay? So you should understand that. Okay, so that's the setup, is we're going to talk about families of types. And the next thing I want to do is a kind of a technical simplification, but it's related to a point I brought up last time, which are the comprehension principles for families. Okay, so which families exist? Which families do we have? Well, to some extent, I'm going to show some primitives, so I'm going to assert this guy as one of them, just because I need something to work with, okay? So we'll have sequences. And then I'm going to show you some closure properties that families have, so I'll mention them like pi and sigma. We'll have some closure properties. And I will, but then I want more than that. And the example I gave you at the end last time, is I want to be able to do things like take if, as I mentioned, if I take if with, I think I wrote something like this, I don't remember, of some x, which is a Boolean, I should be able to say that that's well typed by some sort of if that says math and string here, where I'm proposing that I have a type of string which should not be controversial. Okay, and I can do other examples if you don't like that. So the question is, this needs to be a family of types. Okay, is that a family of types or not? Well, it could be postulated. So for example, I could say to you, from any Boolean, let's say we have Booleans, which are definable, I could postulate, I'll write it as a capital if just to be emphatic, that if A, B of X is a type, okay, provided that A is a type and B is a type. That would be like an example of what I might do. We can get, there's lots of ways to be fancy, but let's just say that, okay? So we can do this. So what it means then is what I really should have written up here is if. And then with the appropriate computation rules, I would write down the computation rules, which are exactly those of the little if. And with the appropriate computation rules, if I plug in true here, this will simplify to nat, that will be 7, and 7 is a nat, and we're good. If I plug in false here, this will simplify to 7, and this will be simplified to string. And because it calculates to string, then it will classify this appropriately as well. So we can do that. Okay, that's definitely possible. I'm using a principle. I hand-waved over a principle that I'll get back to in a minute. So we'll talk about that. But before I get to that, there's one of these chicken and egg things. So I've got to explain something. So you can do this kind of thing, but you're going to have to do it for every damn limb form, at least from all of the positive types. Why? Because positive types are characterized by a mapping out property, and you can map out into not only any given type that comes along, but also the universe of types. Okay? So everything has to get duplicated to account for the mapping out property. So there's a conceptual economy that comes here, in which what we do is we sort of drop this idea, and we subsume the notion of family through the notion of element, by introducing what is called the universe. So what we're going to do is we're going to replace A as a type by, I'll use this notation, A as in U, and then equal types will mean in U. And then I would do the same over here, for example, in U and in U. Okay? And I'll explain what U is in a second. All right, now, so we're going to face an interesting question right this second. So what is U? So notice what I'm trying to do is I'm getting rid of this whole line, all right, really is an instance of that line. So in a sense, I'm just getting rid of this line by postulating that there's a thing called the universe. Okay, so I'm going to get rid of that. The problem is, what sort of thing is the universe? Well, it's a type. But it can't be an element of itself without getting inconsistent. So what we in fact do is we have, an infinite hierarchy of universes. This is an idea that was introduced in Euclid. There's no type judgment. We just have an infinite hierarchy of universes. 1 on to infinity that are cumulative. And I will write that informally, and I'll show you how to write it formally in a minute. Informally, it means everything in U0 is in U1, everything in U1 is in U2, and so on. I'll put that in quotes. Okay? So then what we do is to decide what the types are, I will say things like this. I will say, in any context, that is in, well, I could say U0. And by the cumulativity principle, well, how will I actually say that? So I want to say this. I'll say if m is in ui for any I, then m is in ui plus 1. So if I stick something in the first universe, I stuck it in all of them, okay, by virtue of cumulativity. Okay, so those are cumulativity principle. And then we'll close it up under everything but itself. Okay, so what we'll do is if A is in U0 and B is in U0, then we will say, if you don't mind the shorthand, A plus times arrow B is in U0. And I'll stick 0 and 1, if you don't mind me abbreviating like that, in U0. You know, 2 rules, I'm writing down there. Okay. So that's all those things, and I'm going to put some other stuff in as well. Okay. The advantage of this now is this guy, I no longer need this guy, because I can go back to this guy, because this will be a family by virtue of the fact it will be a family because I will be able to show, given x nat, this thing, it has the type U0. Okay? That's the idea. So that's true because the rules, the typing rules, nat is in U0, well, this thing's in U0 for the sake of the example, and then that's enough to show that this is conditional. So now we don't need these so-called large elims, as they're sometimes called. So we're going to get rid of all that. There are other reasons to want to do this, but right now I'm introducing it as a technical device. It will shortly become a very, not a technical device, but a fascinating object of some fascination. Okay, so the other thing I want to do is, what sort of thing is U0? Well, U0 is in U1, and in general, UI is a type of level I plus 1. So this is the hierarchy. It's inconsistent to have any UI be a member of UI. If you're going to do that, you might as well not number them, and then you can just have U colon U. So the universe is a universe of types, that is, its elements are types, but it's not the universe of all types because we can't have that. This would be a type of all types. Can't have it. That's inconsistent. I won't give you the proof of that, but it's not too hard to do. It's just a version of the Burali-Forti paradox, okay? Because the class of all ordinals behaves in every way like an ordinal. So if you say that the class of all ordinals is a set, so therefore it is an ordinal, then you have an ordinal of all ordinals. And the Burali-Forti paradox says that that's inconsistent. Okay, so let's just leave it at that. Okay, so a similar kind of thing can be done there. So you cannot have this. Okay, and then what we're going to do is we're going to add in. Now I need to account for families. So the universe gives me the ability to start building families. So so one thing I'll put in here is given x and nat, sec of x will also be in U0. So that's one of my comprehension principles for the universe. So I'll have that around for the sake of convenient examples, okay, that I want to do. And now I'm going to close it up under 2 things, which are called sigma and pi. So what I'm going to claim is, and these are the things we haven't had before, I'm going to claim that pi x in AB is in U0, and so is sigma x in AB. If A is in U0, and with x in A, B is in U0. Well, to be honest, here I want to, since it's a closure property, for these, I really want to say at any I you like. This I'll put in the bottom. But when I'm talking about closure properties, I want to say wherever you are, if you have a type like UI mode 1, I think there is one, then you can form this function space. So U0 error 0 is in U1. So I need a more general rule. And so the same thing goes here. So we'll put UI, and we'll put UI here, and this will be in UI. And that's in UI. So this stuff starts to look esoteric in a certain way, but don't worry about it, okay? Because I'm going to explain what sigma pi are just to make sure, in case you don't understand them. They're already. There's a generalization. They're a generalization of the idea of a quantifier, but where we do away with the separation between propositions and types. Like we don't sort of say there's data over here and propositions about them over here, and we keep those apart. That's the conventional first order and higher order logic are like that, okay? We're going to coalesce those things. In the same way that, you know, Turing machine or RAM says the data's over here and the program's over here and the program acts on the data from a distance. Instead, we're going to do the clean, elegant lambda calculus way, in which there's no distinction between the data and the program. Okay, that's the beautiful model of model of computation. Right? So we're using heavily, we're relying on the ideas of Church in the 1930s. It's a curious fact that there's this dichotomy between of influence, and I find it even more curious because in Europe the lambda calculus is sort of king, and in the US the Turing machine is sort of king. But it's the Britisher who invented the Turing machine. It's the American and his notable student Dana Scott who brought lambda calculus to Europe. So that's a funny thing that happened there. As far as I personally am concerned, selfishly, I wish it were the other way around. But oh well, I was born in the wrong place. Okay. So, but it is funny that that's the way it has worked out. So I'm trying to change that stuff. Okay, so what are these sigma and pi's? Okay, so for now, that's all there is to say about elements of the universe until I broach the concept of equality, and then or identification, we'll get to that later. But for right now, it's some sort of technical device that is unfortunately necessary because of the paradoxes that were well known 150 years ago, or not quite 100 years ago, round figures. Were known, so we have to deal with that. So right now, it's like you hold your nose and you just have to suffer. And the truth is, the way we're going to behave is I'm going to act like you is in you. I'm not going to worry about the I's and J's all the time. Okay? I'm just going to write you. And the reason is that there are algorithms to sort it out. And pretty much anything you write down that makes any sense is going to automatically be stratifiable. Okay? In the sense that we have here. And you really have to go out of your way to make something that isn't stratifiable. And if you really want to do that, what you should do is formalize the Raleigh-Forty paradox. So that's what Pollock and I did in 1989, because we were unable to, we implemented this idea of universal polymorphism, and we were unable to get it to say no. Every single example, no matter how hard we tried, every single example, there was some way to stratify it so it made sense. So we finally said, all right, goddammit, we'll just formalize the Raleigh-Forty paradox, and it finally said no. That is not stratifiable. Okay, but we had to go all the way. There was no way that anything natural ended up violating the universe level constraints. That wasn't possible. Okay, sigma and pi, very simple ideas. They also arise in set theory. Many people see them for the first time when talking about topology, because families of sets come up a lot in topology, because that's the way topology are defined. So that's where you might have seen it. But here's the idea. So I've given you the formation rule already somewhere. There it is. Okay, so introduction rule. So the idea is, if uniformly in X, I can give you an element of B. I'll write X here because I'll just emphasize that just to allow it to depend. Then lambda xm is inhabits pi x and B. So that's the pi introduction. Okay, and the pi elimination says if you give me something in pi x and A, and you give me a particular A, so this is an A-indexed family of elements of a family of types, right? So you can think of it like that. So there's a bunch of, for each thing in A, A1, A2, A3, not necessarily countable, I don't mean to imply that, but think of it like this. All right, for all the A's you have here, you have an M sub A4, and it's going to have a B sub A4. M sub A1 is going to inhabit B sub A1, et cetera. So it's going to look like, oops, it's going to look, so you can think of it like that. So this is now picks a branch. Okay, so I pick a branch, and I say just apply M to N, and I get N for X. So here's the important thing, N for XB. Okay? The type of the application of the lambda is determined by what you apply it to. As a special case is, if this doesn't actually occur in B, then you're going to recover the arrow. So it generalizes the arrow. You can think of it as generalizing the arrow. It's a product over a constant family. If all of these B's are exactly the same type, they're all just B, then I'm talking about a lambda term. I'm talking about lambda x m. It's a little x here, and it's A arrow B. Okay, so that's the picture. All right, so that's that. And what is the, we're only going to do now the calculation rule. So the calculation rule is exactly what I said before. N for xb, N for xm, sorry. And of course this will be N for xp. And of course I have to have the context and all these very things. Okay, that's that. The typical, you can state a unicity rule. So this is the beta. You can state a beta. But whether we do or not is, as I say, the calculational equality is quite arbitrary. Okay, so maybe I choose this, maybe I don't. I don't know of any principle that says I should or I shouldn't do it. Okay, it just is like whatever you feel like. Okay, it's a formal system. You do what you want. Okay, so I'm goading you a little bit. Okay, because I want you to think about what we're doing here. As I said, my objective in these lectures is to invent type theory for you, all right, with you. And so I'm trying to make you think about all of these considerations. All right, so good. Okay, so that was that. Oh, then the sigma. So let's do the sigma. The sigma generalizes the Cartesian product to have a dependency as well. I don't want to dwell on these. I don't find them, there's nothing incredibly remarkable about these things. Oh, I will mention to you, though, it's worthwhile in your mind, is considering little examples. So consider examples like this. Pi x in U, x arrow x. It says for every type in the universe U, I'm going to give you an element of the function space. So the identity function will inhabit that. So lambda x, lambda little x, x will be an element of that type. However, so I should put this over here, down there. Okay. But the thing to notice is that it itself, I'm going to have to be explicit now in order to make my point. This will have to be in UI plus 1 or higher. Okay? So that is the issue of what is called predicativity. The whole idea of this stratification was the whole motivation for Russell's notion of type, and it was all to ensure that things were predicative. So predicative means they are stratified in a hierarchical way. It's a semantic issue, and I don't have time, or I don't want to take the time to go into why is that an important issue. It's an important issue. Okay, and let's not, I'm sorry, I can't go into that right now. So what happens with sigma? So what are the inhabitants of the sigma type? Well, they're ordered pairs. Okay, so this would be sigma introduction. And the idea is it's an ordered pair where M is in A. And now here's the tricky part. N is in M for xb. So you can think of this as basically the general sum. It's the sum of all the b sub x's over x in A. Okay, so a picture might help here. So if we picture a family of types like this, if we picture a family of types like this, where I have the base type, which is called A, well I should have called it B, but I didn't, so let's stick with that. And I have a bunch of A's sitting in here, and over each one, that's sort of the picture I was drawing you before, over each one I have B sub x. for that particular x. And over this one, okay, I have, let's call that prime and double prime just to give me some notation. So this will be b sub x double prime. And over here, I'll have another one, and of course, you know, I'm just depicting, just showing you a little picture. And it has its own little elements here, you know. So maybe it has none, maybe that one is empty. Who knows? I don't know. Okay? So when I form the big sum, what I'm doing is I'm taking all of these guys and amalgamating them and recording, attaching to each guy what is it over. So if I put over here a little b in this balloon, when I amalgamate it, I turn it into x comma b. So that's x. And when I have a b prime over here, I turn it into x prime comma b prime. I want to remember where it came from, because if I just slam them all together, I'm going to forget. If 7 occurs in several different balloons, then I lose information. So I don't want to lose any information. So I amalgamate all these things by labeling them where they came from, which then gives rise to a projection that goes the other direction, okay, which sends xb to x and sends x prime b prime to x prime, and so on. Okay? So we can have this projection E. So this big amalgamation is the sum. This tells me the index, A, where does it sit over? And it sits in what's called the fiber of B over that element M. So a way to draw that, once you've done this amalgamation, it's typical now to draw the picture in this manner. Let me write x prime, x double prime. What I do is I squish all that balloon there, I turn it like this. I put up here sigma x and A, B. And over each element, I take all of the elements of that balloon, B sub x, and put them in a line here. And that's called the fiber over x. And all the elements of the balloon over x prime, I put those in a line here. Okay? So this is B sub x prime. And the same thing with x double prime. So I get B of x double prime down here, and here's my A. And then what P does, that projection, all of these guys are over x prime. So everything in this line gets sent here. Everything in this line gets sent here. Everything in this line gets sent here. And the intuition is supposed to be, you know, that the sum of all those lines is the entire so-called total space. Okay? So that's the one rule of sigma, okay, is to give you, to turn a family as a function to a family as a vibration. What makes this a vibration will come up later. It has to do with how these might be connected or not. Okay? So the intuition will be, if x and x prime are connected in some way, which I will explain later, that will induce a thing that sends this guy here. Well, if they're connected in some way, it will send this guy here to this guy here. Or another way of saying it is, it will send this guy over to here, and then it will tell you that these two guys are connected. That's what will actually happen. We'll get to that in a minute. So what's happening is if there's a so-called path from x to x prime, this is so-called a path, then I can lift the path from the base space to the total space by saying it takes this information, takes an element here, sends it over to the fiber over x prime, and then connects them vertically. Okay, so it sort of factors it into a horizontal and a vertical part. Okay, so that's what's going on. So the idea is that the path is being lifted into the total space. Okay, so that's the path lifting property. So we'll get back to that later. Okay, so this is the introduction rule for the sum. So this is the fiber of B over M, and if N is in the fiber, and then I compare it with M and say it's in the total space. That's all I'm saying. Okay? Now, if I have something which is in the total space, then I can do two things with it. There's going to be sigma elim 1 and 2. Okay? I can take its first component, first of M, and where will that be? That will be in N. You can call that tag of M if you like. I don't care. All right? Index of M, you know, you could give it different names, but it's typical just to be boring, call it first and second. The question is, where does the second live? If I take the second component of M, where does it live? It lives in the fiber of the first, of B over the first component. So the fiber is first of M for X and B. This is the fiber over first of M. So the second of M lives in the fiber over the first of M. That is, if I take the second component here, it lives in the fiber in this vertical line here, okay, over what its first component is. The first component is marked there. So that's what I'm saying. And then you have exactly the expected beta-like rule. That's equal to M. I won't bother to write down the types. Equals N. And if you wanted to have an eta-like rule, you'd have the same one I had before, which is the pair first second is equal to the identity. So you could do that if you wanted. Okay, but I'll just stick with the beta-like rule. So that's sigma and pi. Okay. So these correspond to, so by Props' types, sigma corresponds to for all, pi belongs to for all, sigma corresponds to exists, pi. Maybe I should put this in quotes or not, I'll just say constructive existence. I will talk about this issue later, I hope, okay, if I have the time. But it's a constructive existential. What do I mean by constructive existential? Well, I'm not sure whether Frank has talked to you about the disjunction property. Did he do cut elimination for? Oh, he did.
Tomorrow.
Okay. Well, let me just say for the time being, it's an existential quantifier where you're not allowed to lie. If you claim that something exists, you must be able to show me the good stuff. Okay? In other words, it's a notion of existence that is distinguished from something that cannot fail to exist. It's different from something that actually does exist. Okay, it's a positive notion of existence. So I'll call that constructive. You're familiar with those kinds of ideas, or should I mention something? You're familiar with that? Okay, good enough or not? You're not so familiar? Somebody else? If I get two, I'll say something. 2, 3,
I'll hear about it.
Okay, so my favorite example, the one that comes up all the time, is the following little fact, which exhibits the kind of cheating I'm talking about. There exists A to the B, which are irrational. In other words, not in Q. Okay, such that A to the B is rational. First of all, it seems rather implausible on the face of it, if you think about it, because, wow, like A to the power might be rational, that's impossible. Okay? Okay. Well, that isn't the answer, there's nothing to that. But, okay. And now here's the standard thing that passes for a proof. Okay. It's cheap. You won't believe how cheap it is, okay? Have you ever watched these programs about magic tricks and how they're really done? It's really, really, really stupid, isn't it? There's like almost none of the, I know of like one trick that I consider to be quite clever. The rest are incredibly stupid. It's just the magician is extremely brazen. That's the main idea. So I'll brazenly give you this proof, okay? So what I'll do is I'll say, consider A equals B equals root 2. And then you say, well, either root 2, we know since antiquity that those are irrational. That's the point. Okay? So either root 2 to the root 2 is in Q, or it's not. Well, if it's in Q, then I'm done. The answer is root 2 and root 2 or root 2. If it's not in Q, then I say, never mind. Take A to be root 2 to root 2, and take B to be root 2. And now if you just calculate root 2 to root 2 to root 2, sorry to bore you, is root 2 squared, which is 2, which is eminently rational. QED. Now I say, what are the A and B? I didn't give it to you, did I? Okay, it's incredibly cheap, okay? All right? So I'll leave you as a homework assignment because I don't want to get too distracted. Have you ever read Lakatos' book, Proofs and Refutations? Has anybody ever even heard of it anymore? No, probably not. Some people have heard of it. I highly recommend that everybody read Locke's book first semester. Put it under your pillow. One of the things that's very nice is what it is a treatise on proof discovery and proof editing. Like serious proof editing, not acting around with email. So the question that Locke would ask, okay, what does the proof really prove? This is what I will ask you. And I'm going to state it just exactly like that because I want you to discover for yourself a way to formulate what the proof really proves. I claim the proof is full of it, okay? It's not actually proving there exists an A and B, such A and B is irrational, such A and B is rational. It's proving something else. It's a good proof of a different theorem. But by the conventions of conventional mathematics, you're allowed to cover your tracks and claim it's an existential when it really isn't. Okay? So whether or not you accept my interpretation, that's not important. But the thing that is important is that there is a notion of existence which this does not satisfy. Okay? It doesn't come up with the goods. And the sigma corresponds to a notion of existence because in order to give a proof of a sigma, I must actually tell you the witness. Okay? I can't get away with saying things like that, okay, and then being unable to tell you what A and B are. That's disallowed in this study. It can be selectively reallowed, and we'll get back to that later, okay? That has to do with the strictures principle that I was telling you before. Okay, so that was an aside. So that's sigma and pi. So now those are the families we have. We have sequences, sigma and pi. We have all simple types. Okay, and if I'm not forgetting myself, I think that's all I want to include at the moment. Okay, so that's what I'm going to do. So I have the notion of the universe, and that's where the universe, at the moment the universes are a technical device, but they become rather interesting later. Okay, so let me just check my notes to remember that I did what I claimed I was going to do. Oh yes, okay. Now I want to mention the following thing. So the next thing I'm going to mention leads to something very important. So I want to go through this with you carefully, okay? Because it sets the stage for maybe one of my biggest points of these lectures, okay? I'm going to set this up now, okay? So I mentioned before, unfortunately I erased it, but I mentioned earlier when I wrote that thing with if, whose type was an if, I glossed over something, okay? And so I want to make sure that I don't gloss over it. So I'll start with the if, but the real example will involve recursors with the natural numbers. So let me do that if revisited, okay? Okay. So what I want to do is remind you, in simple types, we have the following rule for if. We said, and this is the one you know from every programming language you've ever used. Sorry, let me write it like this. So the Booleans are a positive type, they're the use of sums, 1 plus 1, they have a mapping out property. The mapping out property says if you give me a Boolean, and if mn applied to that Boolean, instantiated to that Boolean, this is the simple type version, has some type C. Provided that M has C, and N has C. In other words, they have to have a common join point. You have to have a single way to describe the join point of the conditional. Okay? All right, so that's the one we saw before. This is the special case of in the case that we're considering the type 1 plus 1. Okay? So that's what it amounts to. You'll notice, by the way, if this is a special case of case, what's happening is I have a bound variable there, but it's not named because it doesn't get to be used. Why don't I name it? Why don't I use it? Because if this is 1 plus 1, there's a bound variable of type unit here, and there's a bound variable of type unit here. And so there's no point in finding a variable to the null tuple. We know it's a null tuple, so we just leave it out. The only reason I mention this is just to dispense with the notion that conditionals somehow, when given endowed with an operational semantics, which I have not done, but when endowed with an operational semantic, that conditionals have some super special status whereby they don't evaluate their arguments. That's BS. You never evaluate underneath the binder. There's an implied binder here, and that's the reason why those are not evaluated, because it's under a binder. You don't evaluate open terms. So then you can get rid of all that, like, list of stuff that goes around. So I'll just mention that. So anyway, that's why I'm doing it. It's a special case of the case. All right, so now that was what we did for simple types. In dependent type theory, we allow it a more rich thing, which you might recognize because it was rediscovered in a kludgy way in another setting. And maybe some of you will say, aha, and I want you to tell me what this is when you do it. So what I'm going to do is I'm going to change this rule. What I'm going to do is I'm going to say the rule for if is going to depend on Z. I'm going to let the type depend on which branch you're in. I'm sorry I erased that previous board. That was a little unfortunate. And here's the way I do it. What I do is I say, if you give me a family of types indexed by Booleans, I'll write CZ just to be emphatic. Okay, so this is a type, so continue. And if you give me an element, this is the part I hand waved over earlier. As I say, it was a chicken and egg problem. I have to, it's hard to know where to start with it. If M is in the true for Z, like that, and if N is in false for Z, that, then I'll say that if, for any Z at all, I will say that if M and Z is in C. But remember, there's a Z in here. Okay? So this is the rule for if in the setting of dependent type theory as opposed to simple type theory, which we were doing before. So in particular, the C could be the example I gave before, if nat string Z. And that will be in U, provided Z is in bold. Right? So that's an example. Now that example is real because I have the universe. I can write the CZ, which is this. And the point is, when I type check the branches, I propagate the fact that I'm in the true branch into the type when I'm checking the then clause. When I'm checking the else clause, I propagate the fact that I'm in the else clause into the type. And then I say uniformly it holds. Okay? So, what's a good name for this principle? What should this be called? I want to give it a name. Think of it from the point of view of programming, or think of it from the point of view of logic. From the point of view of logic, what am I doing? Well, what I'm doing is, and by the way, very often in type theory, really you have to include somewhere what is this family, Z.C will be included as a parameter. And I forgot to mention, that is called the motive. I think Connor McBride invented that term, and it's a great term, I like it, so that's a really nice term. So it tells you the motive for the what goes in the quotes. I'm doing a proof by induction. And this is the motive for the induction, the motive being the thing I want to prove. So I want to prove that for any Z, C of Z is true, which means there's a proof of it. The proof is going to be this conditional. In the case of a Boolean, the induction principle is case analysis. Prove that it holds for true, prove that it holds for false, call those proofs M and N respectively. Combine them, and then I get a proof called if, which is a proof that it holds in general. The mapping out property is a proof by induction. Okay? So this is what it's called from the point of view of logic. What is it called in programming languages that you might know about? That introduced about 40 years. It got rediscovered about 40 years after it was actually understood and used, for example, in New Pro, 30 years. Someone? I didn't hear that. Could somebody relay that? Pattern matching, well, it's related to pattern matching, yes. It's a form of pattern matching. It's a form of pattern matching, and it's what they're called in Haskell GADTs, which are a kludge version of the dependent type element for like if was an example of pattern matching. You want to propagate into the branch, but they don't have this ability, so you use a hack with a type that represents the Boolean. So there's a kludgy aspect to that. Okay? That's what they're trying to do with GADTs. Okay? So in my mind, don't worry about GADTs. Worry about dependent type theory. That's the real deal. Okay? So that's just a little side remark, my personal opinion. Okay, so, but it is undoubtedly a proof by induction. So this is critical. So now let's say, oh, so that must mean that a proof by induction in the ordinary sense of the word must be accounted for also in dependent type theory, and it is, which is there's a different typing rule for the recursor. Oh, okay, by the way. Well, all right, I'll worry about setting exercises later. I will send you some exercises pertaining to this.
Did we, was Z supposed to remain in the environment in the two rules?
What was the question?
Was Z supposed to remain in the environment in the two rules that we just had?
And the previous, where I was, the previous example?
Yeah, on the end.
Well, the substitution principle says I can plug in some n for Z.
No, the line above.
Oh, where are you looking?
Just there's no Z in gamma anymore.
Here?
Yeah.
I'm substituting for Z and C.
But what if Z appears in N?
What
if Z appears in N? Or N?
N. No, I'm explicitly not allowing that because gamma doesn't have a Z in it.
Okay.
Yeah. So I'm plugging that in. Yeah.
Okay.
All right. So I specialize the type before type checking. So the exact same principle applies, and the same description applies, to the revised rule for the recursor. So with simple types, the iterator or the recursor, I'll write it in a very slightly different form that doesn't matter. I gave you as an exercise to show that it doesn't matter. Okay, so I'll write it as x, y, n. I'm forgetting to do what I want to do here. It has a mapping out property. So if you want to reason from the fact that you have a natural number, then the recursor is the way to do it. Okay, and it's going to give me, let's call it, well, in simple types, this was a some fixed type C. And the requirement was that M is in C, and then the slight variation that doesn't matter is I give you the predecessor and also the result of the recursive call on the predecessor, and I give you C. But the iterator, I left that out. But the homework was show that that didn't make any difference. Okay, so I just wrote like that. If you have products, then you're going to have products, so it's no problem. Okay, so what does it look like in dependent type theory? The reason I wanted the slight revision is because I wanted to get the comparison to work. So what I'm going to do now is I'm going to have a family of types indexed by NAT. Okay, so this is going to be in the universe. All right, C sub D if you want, just to be emphatic. Okay, and now what do I want? Well, you're going to be able to guess. How do you do a proof by induction? You prove the base case, which is to prove that C holds for 0. Right? And here, given any natural number n, and the assumption that, oh, let's call it, I'll call it x for z, c, just to be explicit. Okay, so we write that. Assume that it holds for that, then show that it holds for the successor. If you can do those two things, then uniformly in Z, there's our mapping out property and dependent type, then the NatRec of M, X, Y, N, Y to Z is a proof uniformly of that C holds for any Z, for any natural number. That's the rule for dependent type. So again, when I'm checking the base case, I propagate it. If you think of it as a program, then when I'm type checking this piece of code, the type knows that I'm in the 0, I'm in the base case. And when I'm type checking this piece of code, the type knows that I'm in the successor case for something. We don't know what, but it's some successor. That information is propagated so I can get a more precise time. Okay? Or you can think about it from the point of view of logic, and you say, if I want to prove that C holds for any Z in that, It's enough to prove that C holds for 0, we'll call that proof M, and it's enough to hold, assuming it holds for X, that it holds for X plus 1, we'll call that proof N, and then package up that information, and that's proof that holds in general. And so that's your mapping out property. And so this is codifying the idea, okay, that the only natural numbers are 0 and successor of another one, that is the least one. The fact that these are sufficient for that is the statement that it's the least type closed under 0 and successor. This is the universal property. Okay, so that way of thinking I find to be extremely important. Okay, so now comes something interesting, okay, which I want to do with you. All right, so we've got this on the table. We're okay? Reasonably comfortable with this? Okay. Now I want to get back a little bit toward the notion of equality. Okay? So here's what I want to do. So this, I bet you will find this tricky. Okay, so it takes some getting used to. Okay, I'm going to do it. So the thing I'm going to, I'm going to have it ready so that I can write it down. Okay. Yeah, there it is. Okay. So what I want to do, we talked about this issue of equality and about extensionality with respect to the recursor as being something particularly important. So what I would like to do is talk about, I'm going to define, okay, the C in question here. So this is the line that I'm going to focus on right now. And the line I'm going to focus on is I'm going to say I can choose that CZ in various ways. So one example, which is simple, and you can do this as a homework, is choose Z now, the motive, choose the motive to be, sequence of length Z. And then for yourself, write some program. I'd have to think of what it would be a good example. Write a program which has the type for every Z in that. You're going to write a program, okay, that ends up being a sequence of that length, where it varies, okay, as you go along. In the base case, maybe you yield a sequence of length 0, and in the inductive step, you're going to grow the sequence by 1. Write some code and do the type checking. I'll have to think of a specific piece of code for it if you want, but you could also think it up. Okay? My point being is that this is like a programming motivated thing. Okay? And if I have a primitive type family called sequences, I can write down some recursive function over the natural numbers whose behavior, its description of its behavior in terms of its type, varies whether you're talking about the base case or the inductive stuff. So that's a programming way to think about it. Okay? Now, but here's another thing that I can do. Okay? So the idea that I want to get at is that C of Z can compute in interesting ways. So the example here is sec of Z is a built-in notion. So there's no interesting way compute or reduce or whatever can calculate in an interesting way. And here's what I want to do. So, example, I can define EQ, which is named to be suggestive and misleading. Okay, so that's the thing I want to get at. So what I'm going to do is I'm going to write down a relation. I could have written this, I could also write this out, Nat cross Nat. How are you? Okay, that doesn't matter. I'm going to do it in the curved way. But, okay, so what I'm doing is I'm going to write down a binary relation, which has the property. I want it to be such that, okay, there's different ways of specifying it, but one way to do it is that remember what I was doing earlier with plus. I'm going to give a similar spec. If you give me M and M, the same numeral, I want that to be 1. And if you give me different numerals, I want that to be 0, or M is not equal to M. Okay, like that. That's going to be my spec. 1 and 0 are typed. Okay? So what I want is that when the two things are the same, this type is inhabited. When the two things are different, it is not inhabited. Okay, that's what I want. Okay, so first part of the exercise is define that. Okay, and the way you're going to do it is you can just do it like this. I'll write it in this way as recursion equations, and I want you to turn that into using the recursive. So for 0, 0, it's going to be 1. For 0 and any successor, I don't care what, it's going to be 0. So I go by induction on the first argument and then by induction on the second. That's the point. So it'll be an iterative recursive. If you give me any successor and you give me 0, then that's also 0, the type 0. Okay? And, void, the actual void, not the fake void, unit. Okay? And you want it to satisfy, I'm writing it in a way that will suggest how to write the code. Oh, successor of, let's call this x and y. I want that to work out to be, I'm going to think of this as being EQ of x, y. So you see what I'm doing here. So I'm computing a type as a function of two natural numbers by examining the natural numbers and just going through all of these guys, all of these cases. And so for homework, you can write this out properly. In other words, using the recursive and so on. Just be very systematic and it'll fall into place. Okay? So in a language that had pattern matching and nice things that you really want, in practice you would be able to write this as just legitimate code. But I'm trying to get you down to basics. Okay? So this is what we're going to do. All right? So notice in particular the recursive call that's happening here. Okay? Two successors are equal. If this is inhabited, then this will be inhabited, and if this is not inhabited, this won't be. That's the idea. So I'm not computing a Boolean, right? I'm computing a type. So I want a type that expresses that its arguments are equal or not. So the other homework thing I would ask you to do is to show for any x in that, exhibit a term, I'll just put a box here, whose type is, oh, well, I wrote it like that. X in that, whose type is EQXX. This is what you have to do. Okay? Fill in that box. To show me that that relation is reflexive, right? You can also show me that it's symmetric and transitive, but I don't want to be abusive. So it's a lot of work, tedious work, okay? But show that it's reflexive, okay? It's EQXX. All right? So that's the first thing. So I know I'm running a little bit long, but give me a few minutes, okay? I just want to ask you, and then I want to ask you a very important question. Okay, so as you see, is it clear what I've asked you to do, like what EQ is doing? It's a props as types point of view, right? I'm writing down the proposition, or the relation, really, the predicate or relation of equality on the natural numbers. That's why I called it EQ, very cheekily, okay? And now I'm going to, okay, so is that all right? All right? So if you're inexperienced, you're going to confuse this with writing a Boolean test, okay? So one of the things this illustrates, which is something very fundamental that in the world of computer science is confused. Booleans are not propositions. You learn from high school, you learn in digital logic, you learn all over the place to confuse propositions with Booleans, okay? If there's one favor I can do for you, it will be to break you of that habit, okay? In every programming language, there's a function called equal sign, which takes in two things, maybe two natural numbers, and gives you back a Boolean, okay? But that thing called equal sign is a hunk of code, and you have no right to identify that piece of code with equality. This is something that is fundamentally confusing. The equal sign in a programming language is not equality. It's some random library function that has the property that if it yields true, then those two things are equal, and if it yields false, those two things are not equal. But it is not equality itself. And in particular, by some almost unimaginable mistake, the code corresponding to equal sign could be broken. It might get the wrong answer. It is not representing mathematical equality. It's computing a Boolean, it is not computing a proposition. I'm computing a proposition here, a proposition expressing that two numbers are equal. It might take time for this to sink in, but there's lots of things that follow from this. There are mistakes all over the place involving confusions between Booleans and propositions. Okay? All right. The reason is that in classical logic, there are only two propositions, true and false. So then it's easy to confuse bits with propositions. But not in the rich world of constructive logic, in which classical logic is a corner case. Okay? It's a minor side case. I'll show you why that is later. Okay, so now I want to ask you the following question. Suppose f is a function from that to that. At least one person in the audience who knows exactly where I'm going. Okay, so suppose f is a function from that to that. And suppose I have some proof, I don't care what it is, m, the name of it is unimportant, I'm not going to care about m particularly at the moment, is a proof that EQ of, let's say, some x and y. Or if you wish, let's put them as variables, x and y. So what I really mean here is I want to make this okay. I have some particular, so I could just, there's different ways I could phrase this. Let's just write x and y and that. Okay. And I have a proof. I have an element of EQ of x and y. So from an external point of view, by this specification, you would think from this specification that what I'm doing is EQ is expressing equality of natural numbers. Okay? And I have a function on the natural numbers, and then I ask you, is it the case or is it not the case that there is an element, there is a proof, let's just write an underscore, that f of x, oh, I should have given particular numbers. It would be easier for me, then I don't need the context around. So let's say we have a proof of this. Let's just take a particular case. You have that. Is it the case that there's another proof, let's put dash prime, that f of m is EQ to f of m? In other words, in a manner of speaking, and I'm just like a magician, flash pots go off, okay, to distract you, okay? If m and n are equal as natural numbers, and f is a function of the natural numbers, one might expect that f respects equality of natural numbers. That's the flash pot. Okay? Is it the case? Should it be the case? Why or why not? That's what I will pick up with next time. Because this will broach a very important issue about equality. Okay? So think about this. And if you want, if you believe it's the case, then you should be able to show me a proof. That is, give me a proof, give it a variable name. Suppose I have a proof of that. You should be able to write a program right here that has this type using that variable. Right. And then if you can do it, give me the proof. I'd like to see it. That would be good. That would be answer. Well, then you'd be answering the positive. That would be a good answer. If not, you're going to have to give me some argument why. Okay? It shouldn't be the case if you think it shouldn't. Okay, so think about that. So the two things I'm illustrating with this example of writing a very non-trivial relation, because when you write out this code, you'll see it's a chore. Okay? But that's okay because I asked you to do it once because I want you to understand what's really happening. So you should always do that kind of thing once. Okay? Then you can gloss over it. That's the first thing. I asked you to prove a very simple theorem about it, that it's reflexive. Okay? You'll be able to do that. You'll exhibit another program here, which looks like a program that witnesses that is reflexive. And then I ask you whether there is such a program given such a program. Okay? Or a term of that type. Give me a term of that type. Okay, let's stop there.